Hello, students. So, it's time for us to talk about the Twelvefold Way. What is the Twelvefold Way? It has this mysterious, very mystical name, well, I don't know how it makes you feel, but feels mystical when I say it. The idea is simple. There are a bunch of counting problems which are equivalent to problems involving placing balls in urns. Or you could think balls in boxes. Or you could think objects in containers. It doesn't matter. Or you could think taking items from containers, or storing items in containers, or placing them in containers. All of these things are equivalent. And these 12 questions about balls and urns are the answers to a huge number of different counting problems that come up. So quite often, recognizing that your counting problem is equivalent to one of them is a helpful way of solving your problem. What are these 12 counting problems that involve balls and urns? Okay, so one of them is that you have distinguishable balls and distinguishable urns. One of them is you have indistinguishable balls and distinguishable urns, or you have distinguishable balls and indistinguishable urns, or both are indistinguishable. So you might think, okay, how do you get 12 different things out of that? That's only 4. And one thing that you could do if you're trying to talk about distinguishable versus indistinguishable is you could say labeled or unlabeled. Because if you think of things that are distinguishable as being labeled or having labels, then we can go back and forth between them. So we could be putting labeled objects into, so this is objects, and these are containers. So labeled into labeled, labeled into unlabeled, unlabeled into labeled, and unlabeled into unlabeled. So those are 4 cases. Okay, so that gives us 4 counting problems. And in general, we have the situation where there are no constraints at all. We just want to know how many ways could I place, make a number 5 labeled objects into 3 labeled containers. And that's a problem. How many ways could I place 7 labeled objects into 12 unlabeled containers? That's another problem. So each of these are problems, but what we could do is we could add constraints. So one constraint that you might want to add is you might say, okay, well, none of the containers is allowed to be empty. That's a reasonable constraint because there's sometimes where you want everything to be assigned something. Plenty of things in math where you want everything to somehow get assigned something. In functions and all sorts of things, we have these sorts of requirements. So we might also have an extra constraint. So we have 3 constraints. We could say no empty, or we could say each containers get greater than or equal to 1 object. Another one you might want to consider is the same thing. Of course, I'm going to be silly and rewrite the word containers. But okay, get less than or equal to 1 object. Maybe containers can only have 1 object. Maybe it's like jobs and people, and we're not allowed to assign 2 people to the same duty or something like that. All sorts of situations would come up like that. And then finally, we have just no constraints, none. So 4 situations, each with 3 possible constraints, and these together are known as the Twelvefold Way. So without looking at the constraints and without solving any of these questions, let's just make sure we understand what an example might be. So suppose we have labeled objects and labeled containers. So we're talking about the first one. Well, one thing I could do here is I could say, okay, I'm going to have 3 containers, and I have 3 labeled objects. So the containers are labeled too. So these are container, you know what, I could, should I use numbers? I'll use numbers. 1, 2, 3. Okay. So what I could do is I could say, okay, how many different ways can I place these labeled objects into these labeled containers? So one of them would be this, and this would be different because I can tell the difference between 1 and 3 because they're labeled. Okay? Also, this would be different because I can tell the difference between this being blue and yellow here or red and yellow here because these red and yellow are distinguishable. We consider them to be labeled. We consider them to be distinguishable. So this is the first case, labeled objects into labeled containers. I purposely don't want to solve these problems just yet. I just want to make sure you understand what I'm saying. Okay, so the next thing I could do is I could say what happens if I have labeled objects and unlabeled containers. Okay, so now, or you know what, let's do unlabeled to labeled first because I don't want to erase these labels too many times. The paper, take it easy on the paper. So now I have unlabeled objects. These all look the same. I can't tell them apart into labeled containers. So here, now if I have this and I do this, that's the same. I just switch these, but they count only once because I can't tell the difference. These are not distinguishable. These are not labeled. If I put a big label on them, 1, 2, and 3, then I could tell them apart. So now we are in the unlabeled object and the labeled container case. Okay, so now I'm going to talk about the second case there. So now we have labeled objects and unlabeled containers. So now I don't care which container is on the left or which container is on the right. If I have red, blue, yellow like that, that's the same as that because I can't tell the difference between these two containers. You might be saying, hey, professor, I can tell the difference because one's on the left. Okay, but we can move them around all you want. Picture that they don't stay in the same place. Picture that we don't know which one's on the left. They're just containers. So this and this are the same. But this is now different because I can tell the objects apart. I just can't tell the containers apart. And then finally, the fourth one would be something like this, where I have unlabeled objects and unlabeled containers. So something like this. Now, if I do this, it's the same as this. And also, if I switch blocks, let's switch these, that's also the same. So a lot of things are going to be the same in the unlabeled case. As a matter of fact, there's so few ways to do it, because if I do this, that's the same as this, that's the same as this. And if I do something like this, well, it doesn't matter where the 2 or 1 go. All of these are the same. The only other possibility that I haven't done with these 3 here is, that one there. So it looks, I said no answers, but you could see what the answer is in the unlabeled to unlabeled case. So, and then in addition, we could put some constraints. For example, if I say containers get greater than or 1 or less than 1 object here, well, the only way to do that with this number of objects is to put 1 in each. But if I say containers must get greater than 1 object, well, now I could do something like that, but I can't do something like that. No empty containers for that first one, for that greater than 1. If I say containers get less than or 1 object, this is going to have no solution here because I have too many objects. But if I had that, containers get less than 1 object, well, not a lot going on there. And also no constraints what we were doing before. So hopefully you now have an idea for what the questions are. All the questions are, how many ways can we place objects in containers? Maybe there's no constraints. Maybe the containers can't be empty. Or maybe each container can only hold at most 1 object. Those are the possible constraints. And then the 4 cases, the objects may or may not be labeled, and the containers may or may not be labeled. And we use different techniques for different problems in the 12. And I guess we'll look into what some of those techniques are moving forward.